All right, students, today we're going to be reviewing for our Unit 9 test. And of course, Unit 9 covers the last of the parent functions that we're going to be looking at this year, and that would be the logarithms. Okay, so let's take a look. The first thing we looked at was that logarithms have the ability to express an equation in a different notation. Okay, so there is a way to convert an equation from what we call exponential notation to what we refer to as logarithmic notation. Okay, now basically the bottom line here is that any rule or any positive number can be written as a positive base raised to a positive power. Okay, and I gave you some examples and stuff like that. The thing that we probably need to understand, and this is probably what was eluding some of you on the different representations worksheet, is that some of you never bothered to learn what these items are called. Okay, we have some number n that is equal to a base being raised to some sort of a power. Okay, now L is what's referred to as the logarithm, or to abbreviate, the log. Okay, now what we're looking at here is n is equal to b to the L. A number is equal to a base raised to a logarithm or an exponent. Okay, so the alternate way of reading that is the log with base b is, to get n, is L. Okay, and writing that in an alternate format, mathematical format, we get log base b of n is L. Okay, we need to be able to convert back and forth between these two notations, the one at the top of the screen and the one at the top of the gray slider right now. You need to be able to get back and forth between those things pretty fluidly. I would imagine that the test is going to have you do this on more than one occasion, not simply just to convert and then that being your answer, but more so solving a problem and needing to be able to convert in order to actually solve the problem. So this little skill is probably not going to be the focus of any questions, not going to be the goal of any questions, but more than likely this is going to be a tool that will be needed if you intend to actually get a question right. So make sure you can get back and forth between these two formats. I believe the rest of this was just examples. Okay. We had some variables involved. Of course, we could solve for the variables, and that was it. So look back at that video if you are still struggling with converting between logarithmic and exponential format. The next thing we did is we came back and we looked at the laws of logarithms. Now, there's actually several of them, but there's only 3 of them that became our focus for Algebra 2. There's some others, but they're more advanced, so we stayed away from those. Okay. Now, the first law dealt with the situation where most frequently the way we use this law, we had two, like the right side of this equation, 2 logs of similar bases that are trying to be added together. And we learned that we have the ability to condense that binomial on the right into a monomial on the left. Okay, so we could do this by multiplying the 2 arguments together, the m and the n in this case, and that would give us a single monomial term, and that kind of frees us up to be able to do some other stuff inside of a problem. Okay, so I gave you an example on that. Law 2. Okay, again, we more use the right side of this law and then use it to come over to the left side of this law. Okay, and that deals with the situation that we have 2 logarithms of similar bases, and they are being subtracted from each other. So we learned that we can combine those into a single term by turning it into a division problem of the arguments, whatever the first argument is, m in this case, and divide that by whatever the second argument is, n in this case. And again, that allows us to get to a monomial, and then we are free to do some other stuff inside of the problem from there. Gave you an example to go along with that one. And then law 3, we were already at least partially familiar with law 3 before we even got to this unit. And this was the idea that if you have a logarithm working on an argument. In this case, the m is the argument. Okay, if you have a logarithm working on an argument, then you are free to take the exponent of the argument and put it out front of the logarithm like a coefficient, and vice versa. If you have a coefficient out in front of a logarithm, you may move it to the exponent of the argument, and so on. Okay, so that allows us mostly to be able to get an unknown variable out of our exponent by pulling it down in front of the logarithm, or possibly if we are trying to condense the problem in some way and maybe we have a coefficient out in front of the logarithm, we can move it to the exponent and that frees us up to do some other things. And there's an example worked out on that one. Okay, and as we have seen, very infrequently do the laws show up one at a time in a problem. They're just like the laws of exponents. They can show up anytime they want to and in any numbers that they want to. So you may have more than one law working in a problem before you can get that problem solved, and that's just the way it goes. Okay, so we worked one out like that, and you can look back at the video on that if you're still struggling with the laws of logarithms. The next thing that we did was kind of took a little step towards the technology on this. And we've learned a little bit about technology as we went along, but unfortunately the technology is a necessary evil on logarithms because there is some mathematics going on behind the mathematical operation of log. And that math is beyond us. It's more of a pre-calculus level type of calculation. Okay, so we have not spent any time trying to worry about what log is actually doing when we look at log of a number, like log 6. We haven't learned how to calculate that. Okay, so we needed a little bit of calculator assistance to help us understand what's going on. And also we did not understand what these different base numbers meant. Okay, so there's a way to get the calculator to understand. Of course, the calculator can understand the log of a number, but it needs a little help if it's trying to understand the log of some sort of a strange base. Now, we've mentioned it several times before that our counting system here on Earth operates on a base 10 system. No matter what language you speak around the world or how you learned math around the world or whatever, we all operate in a common counting system, and that would be base 10. That is the language that our calculators are programmed in. That is the language that we learn to count in, add in, subtract in, multiply in, divide in, and so on. But if we are not in base 10, then we have to understand that an adjustment needs to be made in order to comprehend the counting system. Okay, so here is the conversion that needed to be made, and based upon some of the questions that I heard yesterday as we were going through the different representations worksheet, there was a strange number of people that still did not know this, and that's kind of alarming, but we do need to know this. If you have log of some weird base b, and then you have an argument n, okay, the mathematics behind this thing is to say that this is a ratio, it's a fraction, and in the numerator of the fraction is log of whatever the argument is divided by log of whatever the base is. And if you can go through this math ratio there, then that is the same as changing the counting system. Now, you guys do not understand the change in counting system. You do not understand what it means when base is not 10. Okay, but the calculator can understand it by this ratio and by understanding what the log calculation is. When you push the log button, the calculator understands it. We don't understand that yet, but the calculator does. So here is how we have to program the calculator in order to understand a logarithm of some type of a strange base. Okay, so we worked out some examples. We showed how this can help us check problems as well. And that was it. Just a quick little supplement on the calculator. Okay, the next thing we did was we started getting into the actual parent function itself. Okay, so beginning discussion here. The unit before this, when unit 8, we spent a considerable amount of time looking at this particular function, which was the exponential function. And as you can see there from the basic parent function 2 to the x, we were looking at a graph that was horizontal going to the left just above the x-axis, and then it crossed through 1 on the y-axis and turned vertical in quadrant 1 and raced off to positive infinity on the y-axis. And its equation was y equals 2 to the x. But as we had discussed earlier in the year, this function, the exponential function, is actually an inverse of another function. Okay, and inverse, of course, hopefully we know this time. Let's see if we can't get these questions right on the test this time, finally. An inverse is basically a reflection through the line y equals x, because an inverse reverses the variables. X becomes y becomes x, and then if you resolve the equation for y, you have the inverse. And if you take this exponential function, y equals 2 to the x, and you reflect it through the line y equals x, we end up with a reflection that looks like this blue line, blue curve that we're looking in the graph right now. Okay, we've got a line coming up from negative infinity just on the positive side of the y-axis. It crosses positive 1 on the x-axis, and then it turns outwards and goes to positive infinity following the x-axis in quadrant 1. Okay, well, obviously these graphs are reflections of each other. Okay, so what we kind of did is we explored and learned that the y equals 2 to the x exponential function and y equals log base 2 of x are inverses of each other. Okay, so you're looking at the two basic parent functions. The red one's the exponential, and the blue one is the logarithmic. Okay, so we looked at some basics there, a little bit of information there. The base number on our logarithm. Okay, hopefully you've gotten adjusted to this by now. Our base number is not going to be a negative number. There is no such thing as a negative counting system. Okay, which is to say you cannot count to negative numbers in a certain column before you reset in a particular column. Okay, they're positive numbers. They may have a negative aspect to them, but the system itself is based upon positive counting values. Okay, so our base number is going to have to be a positive number, and our base number is not allowed to be a 1. If you're curious what happens when the base number is 1, well, if you recycle in a particular numerical column at the value 1, okay, well, basically that causes an infinite feedback loop, and the number races off to infinity in an extreme hurry. But anyway, cannot be a 1, but it's got to be a positive number. Okay, since there's so many potential values for b, the base number on our logarithmic function, that means that we have infinite possibilities for that base. That also means infinite possibilities for the parent function. The good news is that changing the base does not have a whole lot of influence on the graph itself, and we'll talk about that more here in just a moment. Okay, so as we've already saw, our parent logarithmic function, it comes up along the negative y-axis in quadrant 4. It passes through 1 on the x-axis, and it turns outward towards infinity on the x-axis in quadrant 1. Okay, so it's an inverse of the exponential. We've already said that several times. Okay, that means that the domain and range are still very similar as they were with the exponential function, but they are inversed just like the functions are. Okay, so our domain on the logarithmic is going to be from 0, but not including 0. We already said that we can't be 0 on our base. Okay, so 0, and the graph will race off to infinity. And the range, even though the graph becomes mostly horizontal after it crosses the x-axis, it is going to continue trickling towards infinity on the y-axis. So our range is actually from negative infinity to positive infinity on the logarithmic function. Okay, we still have an asymptote running through our graph. Okay, and our asymptote, if you have not figured it out yet, the asymptote will actually match how you read the h value on your equation, but we'll come back to that here in a moment. Okay, and just important to understand that nature of the graph, because when it comes time to graph them, we need to understand which leg of the logarithmic function is going to be mostly vertical, so we can pick small steps as we plug in our x values, and which leg of the logarithmic graph is going to be mostly horizontal, so we can pick more convenient larger steps when we're getting our graphs done. Okay, so the next thing we did, we came back and looked at the equations themselves. Okay, one of the first things we saw, there are a lot of potential variables inside of the logarithmic function. It would look quite scary to us had we not already had several months worth of experience on the parent functions, because a lot of these numbers, except for the base of the logarithm, a lot of these numbers we're already familiar with. They're still in the same places, basically doing the same thing, basically having the same effects with the functions themselves. The only difference would be the base number, and kind of as we've already said, it doesn't really have that much of an impact on the graph. The base can distort or skew the graph a little bit, but mostly the graph is unchanged. But anyway, we took a look at some of the information there. Of course, H and K are transformations within the graph. It's moving our function around in the graph. A and C have reflection properties to them. Okay, if you or the signs of A and C, pardon me, have reflection properties to them, but the A and C values themselves, they are either going to compress or stretch the graph depending on which of the two variables is changed and which direction which value, whether they're getting bigger, whether they're getting smaller, stuff like that. And B, like I said, it does kind of compress or stretch the graph, but it's more of a distorting effect. So we haven't spent a whole lot of time really worrying about B, since we don't really understand the log, the math of log. We don't really understand the base itself. There's really no point for us to spend any time trying to interpret B and what it's really going to mean to the graph. Okay, so we spent some time, we looked at the different variables. Of course, we start off with A. A is the coefficient that directly affects the Y value. Okay, so we should expect that when we change A, we're going to have our graph stretched or compressed vertically. Okay, now the starting point for the graph is A equals 1. Those are those center graphs that you're seeing there. That's the natural shape and direction of the graph when A equals 1. As you can see on the left-hand side, when A becomes a value that's smaller than 1, the graph is not rising or falling from the y-axis, infinity on the y-axis. Really, I'm sorry, let me say that again. It's when A is smaller than 1, the graph is not in as big of a hurry to rise up towards positive infinity or to fall towards negative infinity. On the right side of the screen, when the A value becomes larger than 1, the graph is in a bigger hurry to get to positive infinity or a bigger hurry to get to negative infinity. And of course, when it's a positive A value, as the top row shows there, you are looking at a graph that is like the one that we already saw. It's coming up the negative y-axis and then turning towards positive infinity in quadrant 1. Okay, if the A value is negative, then the graph is upside down. We've essentially changed the y's direction. Okay, so we get a reflection through the x-axis, and the graph comes from positive infinity down the y-axis, crosses the x-axis at the same place, and then turns towards x infinity in quadrant 4. Okay, looked at the B just very briefly. Okay, and you can see that if B is a value between 0 and 1, okay, then the graph is upside down. That has the same effect as changing the A's sign. Okay, so watch out for that. That is a different way to turn the graph upside down. And when B is larger than 1, then we get the normal direction and shape of the graph like you see over there on the right. And to reinforce, we already said that B is not allowed to equal 1, and of course we're not allowed to have negative bases. Those are actually in the imaginary graph, which you guys have not seen yet. Okay, we are in the real graph, and y'all haven't learned the imaginary graph yet. Okay, on the C value, okay, of course, we can change the coefficient in front of x, and this largely has the same type of effect as changing the A value when it comes to the logarithmic function. Again, as you can see in the middle there, the beginning point, the starting point is C equals 1. Okay, and when you get C equals 1, you've got the natural shape and basic idea of the graph. When C gets smaller than 1, again, it has some of the same effect. You can see that the graph is it's closer to the x-axis. Okay, but it has been, it's kind of like it's being pulled outward, stretched on the x-axis, and that's kind of keeping it closer to the y-axis. So as A gets bigger or as C gets bigger, you get this kind of smashed vertically look to the graph. And over there on the right side, when C gets bigger than 1, okay, what's actually happening is the graph is getting squished horizontally, and that's actually making it look like it expands higher up, like it's trying to rise up faster than it should have. Okay, so again, that has the same kind of visual effect. When A gets bigger or when C gets bigger, it looks like the graph is trying to rise up more than it should have. Okay. The rest of this was just going through examples, so please look back at that video if you need more help. And then the last thing we did was inequalities. Before this particular lesson, we did take time and do the cards activity for a couple days in the classroom, and then we came back and we did the inequalities. Nothing really new to report on the inequalities. It's the same old, same old. Okay. Of course, you know that any point that exists on a graph is a solution for that graph, and when an inequality is involved, of course, you have an area of space that contains solutions for that graph as well. Okay, so we talked about the different ways that you can read an inequality and graph it accordingly. If your variable is isolated, well, read the variable. It'll tell you exactly which axis to follow with your shading, and it'll tell you which direction to follow that shading as well. If your variable is not isolated and you think you can get it done easily, well, then get it done and then read the inequality. If you're having trouble with an inequality, or you just cannot seem to get the variable isolated accurately, or you're just scared of it or whatever, pick a test point in open space. Now keep in mind with the logarithmic function, okay, we probably want to pick a point that is basically either over the graph or under the graph. We don't want to get too much sideways with the graph, because you might actually pick a point that is either on the asymptote or on the other side of the asymptote, in which case plugging that point into the inequality is probably going to lie to you, and then you're going to end up with something going considerably wrong. Okay. When you plug in a point to the equation, the inequality, if the inequality likes it, then that means shade towards that point that you picked. If the inequality does not like the point, you will get a false statement out of your inequality after you simplify, and that means shade away from that point. Okay, we worked through several examples on that one as well. The last thing that we did was we looked at the different representations of logarithmic functions. And of course, the different representations is just all the different ways that I can think of that they might try to ask you questions about logarithms. As I stated in class the other day, I think it's kind of a good news, bad news situation. Good news is they're not going to come at you with a whole lot of word problems on the logarithmic function. And that would be because we are simply not developed enough in Algebra 2 to be able to understand what log actually means and what a different base number really actually means. So they cannot put it into sentence or written form and expect us to assemble an equation based upon a particular log or a particular base or stuff like that. Okay, so that's kind of the good news. Bad news is I don't think that means that they're going to leave you alone as far as word problems are concerned. I think it's probably pretty likely that they are going to pull back from Unit 8. They're going to spiral a bunch of questions back in about the growth and decay formulas. Okay, so you're going to need to spend a little bit of time possibly looking back. Maybe you want to watch the review video from Unit 8. It's still posted on Edmodo and on YouTube. Okay, look back at those equations, the incremental growth, the exponential growth. Make sure you remember how those equations work, how to plug them in, what numbers are supposed to be happening for the different rates, okay, and stuff on there. Because remember, rate in the base of a formula, it actually reads different and is written different than rate in an exponent of a formula. Okay, so we need to make sure that we still remember, because once again, we did not do that well on those problems, and their tendency is when we do not do well on particular problems, they're going to continue to ask questions about them until we prove that we can actually get it right. Okay, so if you can have a basic mastery of that stuff, then you're probably in pretty good shape, and the Unit 9 test won't be a whole lot of a challenge for you. Okay, but of course, make sure that you do prepare adequately and come to the test ready to go, and that's pretty much your review.